Hello scientists, we're here to review for the Unit 4 test for physical science. Let's briefly talk about Lab 4.07. In the video, they dropped clay shapes down through a tube of shampoo, which is a pretty viscous, thick liquid, and they timed how long it took to reach the bottom, from a line at the top to a line at the bottom. So this was their dependent variable. How long it took to go through the shampoo depended on the surface area of the shape. There were different shapes and they measured the surface area for each of them. They were all made out of clay, so the density was the same. You can see the different shapes here in an experiment I did a couple of years ago. Each piece of the same density because they were all made out of the same thing. They had different surface areas to create different amounts of fluid drag. That, of course, is a frictional force, and that depends on the amount of surface area. The time it took to settle to go through the tube of shampoo changed due to conditions that varied in the experiment. And when something depends on what you change in the experiment, we call that the dependent variable. So this time to flow through the tube, to fall through, that's the dependent variable in the experiment. If you haven't done that lab yet, you should do that before you take the test. Remember, we were looking at the relationship between surface area of the different shapes and the amount of drag, and that drag slowed the shapes down. The more drag, the slower it went through the tube, and that time was the dependent variable for the experiment. Fluid drag, as we said before, is a frictional force. So fluid drag is friction within a fluid acting on that surface area. It happens if you throw a ball, and air is a fluid as well, and if you throw, say, this plastic ball across the room, the air dragging across the surface of the ball is going to cause some frictional force. So what is pressure? That is a big question that we're asking in this unit. Pressure is calculated as force per unit area. Remember, it's force per unit area, how much something is pushing and how much area. So if we wanted to measure the force on this ice cream lid, we could measure how much air is pushing down on that particular surface area of this shape. And air is always pushing down on you. That's called atmospheric pressure, but that is another lab. Pressure changes with temperature, volume, and depth. So the deeper you go in a lake, you know, the more your ears hurt. And that's because the weight of the fluid on top of you is causing more pressure as you go down within a fluid. Pressure is also caused by the collision of molecules inside the surface of the container that holds the fluid. So if you have a pop can and you shake it up, you're changing the conditions, changing the pressure within that container and changing the number of collisions. An increase in temperature also increases the number of collisions between molecules to increase pressure. So if you take your pop can and you didn't open it and you heat it, which is not a good idea, you're going to increase the number of collisions between molecules and increase the pressure in the can. And the reason we don't do that is because it might explode. If you get too much pressure in a can, it's going to explode. With more kinetic energy, the molecules move faster and hit the sides of the container harder, which means a higher pressure. So when we increase the temperature, we're really affecting the kinetic energy of the molecules. Temperature, remember, is a measurement of the average kinetic energy. If you give the molecules more heat, they have a higher temperature, they have more kinetic energy, and they slam into the container more often and with a harder pressure, with more force. Increasing the number of molecules of air in the container increases the pressure. You know this, when you put more air in your tires, the pressure in your tires goes up. So we can increase the amount of stuff in a container and increase the pressure that way. We also talked about if you go down within a liquid, like go down to the bottom of a lake, you will feel more pressure. So it's a good idea to kind of think of this as a teeter-totter. You can make yourself one of these, and we'll use that to predict some changes in pressure, temperature, and volume in the next couple of slides. So you can see I made a strip right here, and I can use this to make some predictions. Later in chemistry, you'll learn a formula for doing this, but right now, let's just do the simple version. So right now, hold temperature constant with your finger and use this as kind of a teeter-totter. If temperature is constant and we decrease the volume, so you can pull the volume side down, what happens to the pressure side? If you decrease volume, like you step on a soda can and squish it, what's going to happen to the pressure? It goes up. If temperature is constant and we decrease the pressure, what's going to happen to the volume? If you open a soda at the same temperature and all of a sudden the volume gets more, the pressure goes down. Or you decrease the pressure in the can, the volume increases, the soda escapes. Think about it that way too. And speaking of soda, you can see some changes in density and buoyancy going on. I don't know how well you can see it here. Oh, there we go. My raisin here is changing its density. You can try this experiment at home. Just take some kind of dried out raisins. I grabbed these from, yep, there you go. You can see it going up and down. I'll give you some of a reference here. You can take some nasty dried up raisins from your Raisin brand, and they have lots of little crevices on them, and they fill up, those crevices fill up with gas bubbles. The gas bubbles attach themselves to the raisin and change the raisin's buoyancy. So the raisins sink and then they float. So you can try this experiment at home, get some kind of dried out raisins. They have to be, you might want to let them sit around for a couple of days out on the countertop, dry them out a little bit, and then put them in some soda and you can watch their buoyancy change. The reason the raisin sinks is all the bubbles, or at least some of them, pop when they get to the surface. So that's a cool little density buoyancy trick I wanted to show you while I still had bubbles in my soda. So back to our temperature, pressure, volume. If we raise the temperature, both the pressure and the volume go up. So you can just pull your whole teeter-totter up. What happens to pressure if you keep volume constant? You hold your volume, you raise temperature, what happens to the pressure? So you can see the relationship between these two variables. You can also hold pressure constant, increase the temperature, and of course your volume goes up. If you hold volume constant and you raise the temperature, the pressure is going to keep going up and up and up in your container. Now, if the pressure increases beyond the capacity of the container to contain your pressure, then you're going to have an explosion. Not always. I mean, you can change the temperature of a pop can quite a bit and it's not going to explode. However, if you change it too much, it goes beyond the capacity of the aluminum can to withhold that pressure and it will explode. So what happens if we raise the temperature of the air inside the marshmallow? People like to toast marshmallows, and those marshmallows have lots of little gas pockets inside them. If we raise the temperature of the air inside the gas pockets, then the kinetic energy of the molecules is going to increase because we've added some heat energy, and the volume is going to increase. Y'all know, hopefully, if you've toasted marshmallows or watched somebody toast a marshmallow, that they get bigger when you put them in the microwave or you put them over a fire and you heat them. It's because of all the little gas pockets. It's because of this PTV relationship. You've raised the temperature, so you've raised the pressure of the gas inside those little gas pockets, and you've raised the volume too. The pressure, the gas molecules push out on the marshmallow harder, and that increases the volume because it's a flexible container. So hopefully your hypothesis was correct. It was supported by your evidence that you've seen. What happens to the kinetic energy of those air molecules? Well, of course, we increase the heat energy by putting them over a fire or exciting them with microwaves, and so it increases. If you take the marshmallow away from the fire or take it out of the microwave, you can form your own hypothesis of what is going to happen. The kinetic energy of the gas decreases, so it slows down. You're bringing the temperature down, so pressure and volume come with it. If you've ever canned, you know, if you take a can of pickles or some jam out of the canner, the pressure inside decreases when it starts to cool down, and you hear that thunk because the pressure on the outside is now greater than the inside, and it's pushed the lid down. We'll go back to our density and buoyancy experiment here. We've got a couple raisins going up and down now. Definitely, I would give this a shot at home. Clear soda works best, or if you really want to gross out your family, you can use a yellow soda. There are 3 ways to affect the pressure in the container. You can change the mass of the fluid, like pumping more air in your tires. You can heat or cool the fluid, change the temperature. We talked about that, so that's the T in PTV. Or you can change the volume. So think about the 3 ways to affect pressure down here. You can change the temperature, you can change the volume, or you can just add more stuff. The equation for pressure, remember, is force per unit area. That's measured in newtons per centimeter squared in the metric system, or pounds per square inch in the standard system. Now let's talk about buoyancy while we have a little bit of time. Buoyancy, of course, is whether you sink or float, and sometimes an object can do both, as our raisins are doing. They sink and they float because their buoyancy is changing. Generally, buoyancy doesn't change, though. It's determined by the buoyant force on the object. The buoyant force is the difference between the pressure at the bottom of the object, top of the object, pushing it down, and the pressure at the top of the object, pushing it up. Pressure at the bottom of the fluid is always more than the top. So an object in fluid feels an upward buoyant force. And that buoyant force sometimes can change if you've got gas bubbles. That's how toy submarines work. If you put some baking powder in them, they will change their density because of the gas bubbles. The same object feels a downward force because of gravity. Eventually, the raisins are sinking because the bubbles pop and gravity overcomes their buoyancy and they go downward. So whether you sink or float is kind of a comparison of gravity and buoyancy. If the buoyancy vector is bigger here, we can move it up here and compare. Buoyancy is definitely bigger, so this boat is going to float. If your friend convinces you to take on a couple of big rocks or a couple of big anchors, that buoyancy vector isn't going to be quite as big because your density has changed. and you can see that the graph